Welcome you all to this course on electron diffraction and imaging. In today's class, we will discuss about atomic form factor, okay, what is the need for it, okay, how it is derived, and as we know in the formula which has been derived for diffraction, okay, structure factor, we write this with this expression I into exponential 2 pi I HUI plus K into VI plus W into LI V L and WI. Okay. This is summed over all the atoms in the unit cell. Here H, K, L represent the specific plane which is contributing to the diffraction. Okay. For that plane, we sum over all the atom positions, what is going to be the total contribution, okay. That is what this structure factor amplitude what it gives. This is essentially a complex quantity. What is essentially important is that there is a factor which comes F corresponding to each atom position. Each atom position, what F represents is what is the contribution from each atom to the scattering. Okay. That is what essentially we are trying to find out. Just look at a general scattering, okay, before we come to this. So, what is our aim? Our aim is to find out that how this structure factor, not the structure factor, atomic scattering factor is derived. That is what that. Okay. For that we have to understand what is the way in which the beam, okay, the probe interacts with the atoms. Okay. When we look at an atom, how we can consider it? It is essentially a nuclear charge which is there, okay, some charge which is there, and there are many levels at which, okay, I am just putting negative to tell that electrons are at various levels, electrons are revolving around the nucleus. So, this at some finite size is there. Okay. How the probe is going to interact with each of the individual electrons, okay, that is what it is going to determine. Similarly, how it is going to interact with the nucleus. The net effect of all this interaction from each of the atom is what is going to give how much of the beam is going to be scattered by the each atom. Okay. That is what we will try to look at it. So, essentially what we require is that the thing is that when a probe passes through, what is the probability that the probe will be first scattered? That is the information which we require. The probability is a quantification of how much scattering is going to take place. Suppose it is scattered, what is the angle through which it is scattered or which the probe is deviated, that is the information. Another information which we require is average distance the probe travels between individual events. Okay. What are the types of probes which you use in diffraction? X-rays, electrons and neutrons. Okay. What we have to find out is that how the atomic scattering factor, okay, is going to be different for these various probes for the same atom. Okay. That is what we will try to find out. That is for each atom, depending upon the probe, is it the same or what sort of interaction takes place, okay. What sort of interaction the probe has with the electrons or with the nucleus. Okay. These are all the information which is necessary to decide what is going to be the atomic scattering factor. Okay. Let us look at what is the scattering phenomena. If you look at X-rays, X-rays are electromagnetic radiation. Okay. It has an electric field and a magnetic field which is associated with when it propagates, and the electric field and magnetic field is fluctuating perpendicular to the propagation direction. When this X-ray interacts with an electron, okay, it could be an atomic electron, it could be any electron when it comes close by, what it is going to do is to make the electrons oscillate. Okay. If it is an electron which is a free electron, it will oscillate with the same frequency as that of the incident probe, the electromagnetic radiation, and then it will be re-radiated because it is an essentially a electron which is oscillating. So, electric field, when the electron oscillates as an oscillator, okay, the electric field is continuously going to change, and this is called as a Hertz oscillator. So, this is the way in which electrons. Okay. What is going to happen in the case of an atom? Okay, there will be a restoring force will also come into the picture. This we will talk about it a little bit later. So, what happens in the case of an electron? If it is an electron which is interacting with an electron, now it is a Coulombic interaction between the charge which is important, whether it interacts with the nucleus or whether it is in that electron. If it is with the nucleus, an electron interacts, it may be an attractive force. If it is going to be with a electron, it is going to be a electron-electron, it is a repulsive force. Okay. And this depends upon how much the electron is going to come close to the nucleus. That is, if the electron, the incident beam is going to be here, or when the incident beam is trying to enter here, depending upon that, these forces also, Coulombic forces also, potential will change. Okay. If you look at the neutrons, okay, how neutrons interact with it? Neutrons are essentially a neutral particle. Okay. So, it is not affected by the charge distribution. Its interaction is mostly with the nucleus of the atom, and we know the size of the nucleus is very small, and the interaction takes place, okay, due to both. With the nucleus, that interaction is essentially, it excites the nucleus, okay, and then it can come to a ground state emitting radiation. And another way which can happen is that there is a spin which is associated with the neutron, which can interact with the electron spin. That is how it can give information about the magnetic state of the material, or the magnetic structure information we can obtain. Okay. Similarly, gamma rays also have very high energy. Okay. They can also essentially resonantly excite a nucleus, and which can be later radiated, but we will not be talking about these aspects because we will be considering for diffraction only these three aspects which we will be looking at it. Okay. Let us look at the scattering. What are the types of scattering which we know? We know that the scattering can be coherent, or the scattering could be incoherent. When do we call a scattering a coherent scattering? Scattering is coherent when, if this is the way one wave propagates, another wave at another comes, okay. If there is a phase relationship between both the waves, okay, exactly at the same phase, or there is a phase relationship, or we can tell that phase relationship exactly what it is going to be, then we can say that it is coherent. If this phase relationship is random, then we call that beam as incoherent. Okay. So, this is talking with respect to the type of scattering which it can take place. Another is the scattering itself could be either elastic or it could be a inelastic scattering. Elastic scattering is one in which the energy of the probe remains the same before and after scattering. Inelastic scattering is in which the energy of the probe is different before scattering as well as after scattering. There is a difference is going to be there. So, these are all the four terms which you can see. So, in any scattering, it could be a coherent scattering or an incoherent scattering. It could be elastic or it could be inelastic. We can have a combination of all these. That is what. So, the scattering can be coherent, elastic, and that is what we consider in the case of a diffraction. Diffraction is essentially nothing but a coherent elastic scattering. If the scattering is coherent but it is inelastic, that is what we call it as a phonon scattering, where some energy is lost, but still we can get information about the lattice vibrations and all this, we could get it from this. Okay. The other is it could be incoherent, okay, as well as inelastic. That is what we use for spectroscopy. There what happens is that the beam as such interacts with sample randomly, okay, and then it loses some energy, specific amount of energy, and comes out with some energy in random direction. Okay, there is no correlation between the direction in which the scattered beam comes. Okay, but this energy which it has lost, that could be used to get information about the chemical identity of the atom. We can get this information. Okay, these are what is used. This is what is used in spectroscopy techniques. Another is the beam itself. Okay, it can interact incoherent, but the scattering could be this one. This is what it happens in the case of when we try to look at disorder in the material. It could be a positional disorder. Okay, especially positional disorder is there. Atoms are displaced from its site, so it need not be a coherent scattering. Okay, but the scattering is still elastic. Okay, these are all the various types of scattering which we can do. Because why I brought in these terminologies is because we are talking with respect to diffraction, where it is essentially a coherent elastic scattering. Okay, for a coherent scattering, okay, what is that? What we can do is, if we wanted to find out, finally when we measure, it is the intensity which we measure. Okay, so the intensity is nothing but, we generally write it in the, if the amplitude is written in terms of a complex term, we write it as psi star. Okay, complex conjugate if we take. So here what is going to happen is that in this particular case, okay, when it is coherent, we first add the amplitude and find out the net resultant amplitude. Okay, this can be taken in the terms of we can express each of these psi in terms of an amplitude A into e to the power of I theta, okay, or we can represent it in terms of a vector diagram and find out the resultant. There are many ways in which it can be done. Okay, then once we have that total amplitude from the psi star, we can find out the density. Incoherent scattering is where, since the process itself is incoherent, for each of the process we find out the psi star for each individual event and add all of them together. That gives rise to a total intensity which we get it. Okay. For diffraction, essentially it is a coherent elastic scattering which we consider diffraction. So we have to add the amplitudes together and then find out the intensity. Okay. But when we take when we are finding out the intensity, because that is what is a measurable quantity, okay, we find that the phase information is lost, because in a complex conjugate term when we take it the product, the phase information cancels out. Some of the terminologies which are required regarding the scattering, because this, what does this F means? This is essentially corresponding to some scattering cross section. Okay. Scattering cross section just tells how much of the incident beam is scattered in a particular direction. That is what essentially that information is given. Okay. Essentially scattering means that effectively what the target does is that when the beam passes through the sample, some area of that sample, suppose we have a sample, this is okay. If the beam is entering like this, okay, if this is the incident intensity, if this completely out, the intensity which comes out remains, that's it's the same as the incident intensity, when they can say that it is totally transparent. Okay, there is no scattering is taking place. If there is a reduction in intensity, then we say that some intensity is removed from the primary direction or in each direction if you look at it, and that is what essentially then we say that scattering is taking place. This can be expressed in terms of what is called as a scattering cross section. There are two terminologies which we use. One is a total scattering cross section, which is does not differentiate between how the scattering varies from region to region. Okay, that is what one is. And another is differential scattering cross section. Okay. In the case of light, suppose we consider that there is a bulb which is there kept at this center. Okay. This bulb is radiating light in all these regions. If you try to find out at some particular distance from it, if we are trying to find out what is going to be, it's uniformly it is coming. Okay. That is what the total scattering cross section we can, it will not change as a function of distance anywhere here, it is going to be the same. But whereas the case of electron scattering, if you can see that in forward direction, as the angle of scattering changes, we find that there is a change in intensity. Then we should know how it is changing as a function of angle. Then we have to use the term differential cross section, and that is generally written as d sigma by d omega. Okay. Omega is the solid angle which we are taking on the surface of the sphere which we consider. Okay. As an example, if you consider it, okay, this is what I have done. In this, suppose we say that some regions are essentially opaque, then what it can happen is that the total intensity of the transmitted beam is going to come down, and if it is an opaque object and beyond which there is no interaction with the matter, if you consider it, then what is going to happen is that the total area of this itself will decide how much of the intensity is going to be cut down. Okay. Per unit the scatterer, if you consider it, okay, that will turn out to be some factor of r squared. It is an area. Okay. That is essentially what it is written generally for a circular one. This can be written as pi r such. So, this is how it is, and r is called as the scattering length. Okay. So, what is essentially important here we have to remember is that the scattering is essentially over a surface when we consider it, whether it is a sphere, okay, or if we consider effectively from the sample how it is going to change as a function of distance, is that is what we are trying to find out. Okay. And what is the effective area over which it is scattering the beam away from, okay, that is what is defines the scattering cross section. An example which we can take for differential scattering cross section is given here. That is, this is an effective area which we are sigma, and if you look at this region, okay, the beam which is entering, it is scattered quite a bit, okay, maybe an electron close to the nucleus, and from here if you look at it, it is less, and here there is no scattering. So, if you look here, the total scattering cross section we have to integrate over the full area, okay, but it has to be considered, okay, at each point, and then it has to be added together, and that is equivalent to integrating over the full area of the sphere. Okay. The same way you can consider, suppose electron is getting scattered into a small region. We wanted to find out what is going to be the scattering distance. This is the sort of formula which we can write. It is a quite simple derivation. Okay. And now you can see that the d sigma d by d omega, here if you look at it, this depends upon the angle of scattering also. And as I mentioned, okay, if you consider an electron which is being scattered and it is with an amplitude E0, because electric field is E0, from a point it is getting scattered, okay, at some distance, like from here it is getting scattered, at a distance if you are trying to find out how it is going to, the amplitude turns out to be E0 by r at that point. This is because the intensity, if you consider I, equals I0 by 4 pi r squared, any point on the surface of that sphere. So, from this the amplitude is square root of that, that is how we are taking. So, essentially the electric field at the any point on the surface of the sphere, if you consider, this is proportional to what, that proportionality constant, that is what is going to is the atomic scattering factor. Okay. Suppose it is isotropic scattering, then d sigma by d omega, it will be a constant, it will not be varying as a function of angle. Otherwise, we will be writing it as, here if you see it, we are writing it as d sigma by d omega is equal to K0 and K are essentially the incident beam direction, and K is the scattered direction. So, it will be varying as a function, that has to be that average which we have to take it, that magnitude is given. Okay. If you have to find out for a full atom, then what we have to do it is for each individual electron, each one of them where they are present, we find out the scattering, then add all of them together. Okay. The whole question which comes is that if I take it for one electron and for each of the electron I find out the contribution, add them together, okay, is it going to be the total sum Z into the scattering contribution for each of them? That is what the question is for coherent scattering. Okay. This we will look at it. Okay. So, this is what I have just calling this as a length scale. Okay, essentially like one electron, if you consider, it is like a point from which a scattering is taking place, okay, scattering of probe by an electron. Another is the sum total, that is if an atom is there, okay, from here at this particular point we wanted to find out if it is the plane wave which is coming, it is getting scattered from this as a spherical wavelet in all this direction. Okay. This wave also will be coming, this will also be coming, meeting at this point. Okay. Then from each electron there is scattering which is going to take place. Okay. All sum total what it is going to be, that is what we call it as the atomic form factor. Okay. Then the next information which we require, once that we have, then using this formula we can find out what is going to be the scattering of probe by atoms, okay, in the unit cell. All the atom together, what is going to be the scattering contribution, that is what essentially F represents. That part of it we have already looked at it. So, what we have to look at is only by the electron and by all the atoms in the all the electrons in the atom, how they contribute to the scattering. Okay. Then another is that from the sample, when we have to get that information, then we have to look at what is the volume over which the beam is falling and the number of unit cells are there, take that contribution also. Then we can tell that when a beam is falling onto a sample, what is going to be the intensity of the scattered radiation, we can quantitatively determine, or whatever we have experimentally measured, theoretically we can derive a formula which will quantitate this is the value which has to come. Okay. Another is in some material density variation can occur, this gives rise to some small angle scattering. This is not very much important for the scope of this lecture, so I will not go into the detail. Okay. So, this probe we could consider generally, okay, two types of probes which we use, okay, neutron, three types of probes which are being used, X-rays, electrons and neutrons. But in any laboratory, X-ray and electron microscope are common facility, so that can be used in a lab, but neutron requires some special facility, only at few places it can be done. So, I will spend more time, and X-ray is the most common one. So, I will start with X-rays first. Okay. Let us consider the case of an X-ray beam, okay, which is traveling in a, this is X, okay, Y is a X-ray beam is assume that it is traveling in this direction. Okay. At the point at the origin, it is seeing an electron, and you know X-ray is an electromagnetic radiation. It has got an electric field and a magnetic field associated with it, and the electric field, if you consider, it will be in these two, it will be essentially assume it is in this direction. It could be randomly any orientation which can have perpendicular to it, then we say that it is an unpolarized one. If it is polarized, the electric field is in a specific direction. Okay. In this particular case, okay, we wanted to find out at any particular point, okay, with respect to this electron which is there, okay, maybe take, let us take in this plane itself, X is Z plane as an angle 2 theta, how it is going to, the intensity is going to vary. This was calculated by a classic formula which was derived by classical theory, classical electrodynamics by J. Thomson. Essentially the answer turns out to be I equals I0, E is the charge of the electron, R is the distance where it is going to be, m is the mass of the electron, c is the velocity. This one is essentially giving the with respect to propagation direction at what point we are trying to measure it. Okay. So, if we try to calculate, and in this specific case which we are considering it, okay, this angle is going to be 90 degree. So, this will turn out to be 1, and from this if we know it, we can calculate what is going to be the amplitude. Okay. It's a function of time. If we take it, this value if you consider it, this turns to be E squared by mc squared. Here what we assume is that it is a very high energy X-ray which is falling onto the sample surface. Okay. And one can see that that is a negative one comes. Okay. That means that if you look at that amplitude, one is negative of the other. Okay. That is very important, because when we look at the intensity, we do not see this effect. Okay. And another important is that this factor E squared by mc squared, this is what in the case of an electron scattering factor, I will call it as an Fe, that is scattering factor, like an atomic scattering factor. This is a scattering factor where an individual electron, this value turns out to be Fe. Okay. If you look at it, this is a very small value. Okay. So, the intensity of the radiation is going to change considerably. Okay. And the unit, if we look at it, this has to be, since it is here it is electric field, this is also an electric field, this has to be inverse of R is what this F has to be. Okay. Is it clear? Okay. That is what I have written from a single point, okay, single electron. And in this particular case, okay, if we are looking at a scattering from this electron, okay, this angle is continuously changing, then that brings about a variation in the intensity. Okay. So, essentially what is going to happen is that the total intensity, if we calculate, that is a term due to, because this electric field can be split into one in this Ey and another is in Ez. Okay. The effect of both of them, okay, onto this beam, we can effect of both of them, okay, on the amplitude at this point P can be, and this is the sort of a formula which will turn out to be, which depends upon this angle cos theta. This is what we call it as a polarization formula in X-ray diffraction. Okay. Now what is going to happen is that in that formula, if the beam is travelling in this forward direction itself, if we consider it the same direction, then what is going to happen, this theta value is becomes 0. So, this becomes the same as the intensity. That means that irrespective of whatever be the electron in the forward direction, intensity remains that same, it is the same. Okay. That means that it is going to be in phase, they add together from. So, that is essentially what is being shown here, is that if you look an electron which is here scattering in the forward direction, okay, the path phase difference, if you see, it is going to be 0 for all. So, all the intensities add together. So, it will be the same as that of the primary beam. Okay. For any other angle, a path difference which is going to come, which depends upon the angle theta, okay. And also it depends upon the theta, essentially depends upon the delta k value. Okay. If this is the k0 and this is k direction, this is where the theta comes into the picture, and also the wavelength of the radiation which comes. Okay. Then what is going to happen is that a phase which is being introduced, depending upon the phase of, so from here as well as here, if an electron is this electron or this electron each scatters, when we find out the amplitude at some specific point, add them together, okay, with the phase we have to see it. So, it is not that the amplitudes directly add together. So, the net amplitude is not going to be a direct sum of the amplitude of each individual one. So, that is what is essentially given by this formula. Okay. And this is how we define the structure factor, and this can be looked at it one way. In an atom, if you consider it's a nucleus and surrounded by electrons which are there at different distances from the nucleus, electrons are situated. So, the electron density we can see it, and if you wanted to average out, not take individual electrons, we can use that density variation okay, instead of individual. That is what essentially is being done. E to the power of delta k dot r, that is what essentially it is going to determine, okay, how much is this variation which is going to be. Okay. If we try to plot this, okay, for a specific value of lambda which we take it, now you can see that this has been taken for copper k alpha copper. So, when the angle of scattering is 0, its maximum, okay. As the scattering angle increases, one can see that the F scattering contribution from the atom is going to get reduced, correct. So, this is what it has been all added together. So, this is what this value which we call it, okay. So, this is essentially is in another way in which it is defined in the book is that if all the electrons which are there taking the phase factor, if all of them are put to the center, okay, what is going to be the contribution which is going to be with the phase factor. That is what essentially what we are doing it to one individual electron. So, you can see that as a function of, so how we can write it, sin theta is one and another is this path difference depends upon lambda also. No, not the path difference depends on lambda, okay. The phase difference if we consider it, okay, path difference also is there, that angle also has to come into a picture. That is why we write sin theta by lambda which we take it, a normalized one. And now you can make out that this is how it is varying. So, that means that when HKL reflection we are going to particular specific HKL reflection, we are looking at the diffraction which is taking place. Depending upon that angle at which we are getting the diffraction peak, the atomic scattering factor which we have to use, we cannot just use the atomic number. It has to be calculated for each of the element and we have to use that value, okay. That is what it is being shown here in another way. This is k0, this is k, the values are fixed and at some particular direction, okay, delta k if we take it, this is corresponding to this determines what the 2 theta angle is going to be, okay. If for the same wavelength, if it is a small size of the atom, okay, then what is essentially going to happen is that the path difference which atoms from here as well as here it will introduce is going to be very small. If the size of the atom is large, then for the same radiation the path difference is relative phase error is going to change. Depending upon that, the value of atomic structuring factor also will change, okay. This has been calculated and I had just taken from the many other books where the values are standard tables which are given, okay. Here you can make out that what S represents is nothing but sin theta by lambda, okay, for various values when it is going to be 0, okay. When the theta is 0, this is what the value which is, it is almost correspond to a atom, the number of electrons which are going to be there in the atom, okay. Suppose the atom is ionized, okay, then what is essentially is going to happen is that the number of electrons are going to be less, okay. So, essentially the atomic scattering factor is going to be different for atom and then ion, okay. But one should remember that since the electrons, it is an electron with the photon interaction which is taking place, okay, the number of electrons only determine, we can assume take the nucleus, the same electric field, okay, that photon it comes very close to nucleus, then what is it going to happen? It can make the nucleus also move, but the size of the nucleus is so large that the amplitude is going to be very small, okay. So, we may not see the radiation if we look at it so weak that we can ignore that part of it. So, essentially now what we have to consider in the case of an X-ray is only the electrons surrounding the nucleus is what is contributing to atomic scattering factor, okay. So, now here if we see this, okay, as the atomic number increases, the F also increases, and as the it gets ionized. Okay, suppose the atom is ionized, the number of electrons in the atom in the ion is going to be small. Depending upon that, there is going to be a variation. Okay, now if you can see that as far as this is concerned, but as we go away from at different angles, okay, then there are some subtle differences which we will be seeing it. Okay. But this also could be used to get some information about what is the state in which that element is given, but the effect is not that drastic here. Okay. But between atoms and ions also there is going to be a difference in that. So, depending upon that, we have to choose that specific value of atomic scattering factor. Now, what is essentially important is that so far we considered with respect to very high energy X-rays is falling, okay, the atom, and how do we say that energy is high? It is like suppose we look at that atom, that K alpha electrons are occupying the K level. Okay. If that electron is removed, what is the energy which will be coming out? That is where the X-ray energy which it can come. That is the frequency with which that vibration can take place, and that is going to be very small. Binding energy of the K electron is much small compared to that of the energy of the incident X-ray. Okay. But what is going to happen is that different type of atoms, okay, contains electrons at various energy levels in each atom, and their binding energy is going to be different. That means that we have to consider cases where, okay, as a function of energy of the incident radiation, is the atomic scatter factor is going to be the same, or is it can change or not. That is something which you have to consider for X-rays. Okay. That is what we are trying to look at it. That how we can do it is that electron is bound to an atom. The K electron is bound very closely, strongly compared to an electron which is outside. So, when that incident X-ray beam comes, and if it is trying to make this electron oscillate, there is a restoring force also will be coming from this. Okay. So, then if you write a differential equation for that incident wave with respect to, this is the sort of a differential equation which we will be writing, this is the restoring force. The solution to this gives what sort of displacement with which it will be, time with which it will be changing. This is what essentially. So, here one is a resonant frequency of the electron is going to come into the picture, which is dictated, okay, by the type of the atom, okay, and another is the incident frequency. Okay. So, if you look at the electric field, also similar expressions will come. Okay. Here three cases which we can consider. One which is very high, another case which is the incident energy is very small compared to that of this one. The third case is when the incident energy is very close to each other. The incident energy and the natural frequency of that electron is becoming almost near to each other. This particular case where it is concerned, that is the case which we have when the incident energy is very large, okay, compared to that, then it is very similar to that of a free electron, okay, the restoring force. Then this factor we have already taken into consideration now. But what is essentially is going to happen is that when it is going to be high, this is a case which we can take it is that suppose I use copper K alpha and I am trying to look at germanium which is larger, okay. Then what is going to happen is that with respect to K level, if I consider it, okay, K level has got a higher energy, so it cannot frequency is high, whereas for all other levels LL level and all, energy is going to be very small, L alpha. So, in that case if you look at it with respect to others, it is L levels and all electrons which are going to be there, the energy of the incident radiation is high, the other one the incident energy is small compared to that. In this case, if you look at the amplitude of the scattered wave, it is going to be positive. This is something which one should remember, okay. And it is going to change with respect to the essentially the ratio of these two which decides. Interesting part is when it is going to be very nearly the same. Since this equation itself has got it is a complex function, we can write it into two terms. Okay. This is essentially simple mathematics. So, it will turn out to be fxl dash and another is the I, the complex the imaginary part fxle. These two terms are going to be there. Essentially what is going to happen is that these factors are now going to change. Let us assume the case with respect to copper K alpha itself. Okay. Suppose I take the case of cobalt, okay, an example which I consider it, because then one will be able to understand it much better. K alpha energy is 8.04 keV, whereas for K electron binding energy in copper is 8.9. If its sample is containing nickel 8.33, so it is higher. Cobalt if you consider 7. We know that if the incident beam has got a X-ray has got an energy which is very close to that of the binding energy of the electron to that level, it will be absorbed and re-emitted with that energy. So, this we call it as a fluorescence which will be taking place. So, the incident electron which is available for now scattering to take place, their intensity is getting reduced considerably, correct. So, for all these elements, if we consider it, electrons are 1.1 keV only or less than that. That means that compared to this, K alpha energy is very high. So, only copper K alpha energy is very high. So, for the incident beam, what matters is with respect to cobalt. Suppose an alloy is nickel cobalt or nickel iron or nickel chromium, then what is going to happen is that the atomic scattering factor is going to be different. Though if it is high energy, what the value is, now it is going to be two different values. And this is what is written here as Fx equals Z plus another factor f dash plus I, and we know that depending upon if lambda omega is slightly greater than lambda r, or omega is that is lambda is if it is slightly less than lambda r, the resonant frequency, then this term is going to be negative. Okay. So, now if we look at the atomic scattering factor, it is not going to be that same. Otherwise, it is only the z which we consider when it is high energy. It is varying with respect to atomic number, no more that happens. This is what we can see in this case, that f dash there is a sudden dip where it becomes negative. And if we look at that f2 dash, this also has been calculated, you can see that for the same copper, if you use copper K alpha, okay, for nickel one it is reducing and another which is increasing. So, the net atomic scattering factor changes. This is what is called as anomalous scattering. This anomalous scattering could be used, okay, to find out ordering in materials. That is, if the elements have got the atomic number which are close by, okay, if we are not able to differentiate between them, suppose an ordering has taken place, by using an X-ray which has an energy such that it is above K alpha for one and less than K alpha for another, okay, then artificially we can change the atomic scattering factor, and that means that the superlattice reflection intensity, when we look at it, we write it as Fa difference Fb, and if A and B, these two values are close by, then it almost turns out to be 0, like that of a disordered material. We could not see that order is there. By artificially changing these values, we can still find out information about ordering. Okay. This clear? So, in short, if you look at an X-ray scattering, okay, atomic scattering factor in the forward direction, if you consider it is proportional to Z or equal to Z, okay. But for all other angles, we have to use the table to find out what the value is, and that has to be used. Okay. Essentially decreases with increasing the angle of scattering. The number of electrons in any atom, okay, only determine the atomic scattering factor. The nucleus has no effect. What is the information which we get from each of these experiments? That is, suppose we use X-ray as a probe, the information which we can get it is essentially electron density distribution. Or electron density map on the sample which we can get it. If we use electron as a probe, the information which we get is essentially potential distribution in the sample, because it is essentially the Coulombic potential with which the electron is interacting. Okay. So, how that varies in that sample, that mapping what is being done. Whereas, if we look with neutrons, it talks about the nuclear charge. Okay. So, how it is getting distributed? Suppose there are two different isotopes are there for the same element. Each isotope can have a different type of atom scattering factor, and one could be positive. Only in neutron you find that another could be negative. So, that means that essentially if it comes like this, in one case if it is scattered, another it may be scattered in this direction. So, this sort of things also have positive and negative atomic scattering factor is possible, okay, with neutron. So, even isotopes, if they are present, we can find out how they are distributed in that sample. That information neutron can give, no other technique can give. Okay. Similarly, that is isotope distribution. That we can get. Similarly, what can happen is that when the magnetic, since it has a magnetic spin associated with it, how the magnetic moments are aligned, okay, that distribution also we can get it using neutrons. Okay. Whereas in this case it is only the electron density distribution. So, depending, this is what is the sort of an interaction which is taking place. That interaction is with respect to, in the case of X-ray, it is only with respect to electron. So, how electron density varies, that distribution comes. In the case of no, that is in the case of X-ray. In the case of electron, what is essentially is going to happen is that it is interacting, the Coulomb interaction with the positive charge or the negative charge or the screen potential, what it is going to be there. Depending upon that, it will give information about how the potential distribution is going to take place. Neutron has got many more information other than, but it does not talk about any of these things about potential distribution. It talks about with respect to a nucleus, isotope distribution, then magnetic moment, how it is getting distributed. Okay. This sort of information we can get it. Okay. So, essentially from X-ray diffraction, the information which we get it just tells about how the electron density distribution is varying in the sample, and generally it peaks around the atomic nucleus. That is the way, that is the information which we are actually getting it from an X-ray diffraction work. Now, let us take the case of an electron. In the case of an electron, what is the sort of an interaction which is going to take place? We could understand what is going to happen in the case of an X-ray. In the case of an electron, it is essentially a interaction between the two charges, the charge of the electron, charge of the nucleus, and the charge of the electrons which are there surrounding the nucleus in the atom. This is essentially a Coulombic interaction which has to be considered. So, the structure factor, when we consider, if we look at the scattered intensity, we can write it is proportional to some term, okay, for each electron, and that depends upon the distance where it is going to be e to the power I k r by r minus r dash, because this is essentially from here, okay, the primary beam when it is coming electron, the plane wave when it is coming and hitting it here, spherical wave is being emanated. So, what is going to be the scattered intensity at this particular point? This is r minus r dash. This is essentially what it has been given. This has to be summed over all the for each electron, and together then we get it. With respect to nucleus also has to be taken into consideration. Okay. The way in which it can be done is that rigorously, if you try to want to find out, it is essentially the Schrodinger equation, we have to use it. It is in a potential field, that is a nucleus is there, it has some Coulomb potential, that a high energy electron is coming, how it is going to interact, that we have to write, and the solution will turn out to be, okay, is this sort of a form. Okay. What is essentially important? This is in the integration, there is a V atomic potential which comes as a function of R, and e to the power of a delta k dot R. The nucleus itself, when these electrons, they are going to screen it. So, the nuclear charge which the electron, depending upon where it comes, is going to be different. Okay. All these factors are coming into the picture. Suppose we take as like a density, this potential also is going to vary. We can write this as potential at different points, okay, into this factor which we can write it sum, and essentially that sum, if you integrate it, this sort of an expression will come into the picture. Okay. The same way we can write it for X-ray also. X-ray, then the density at each of the point, okay, from the nucleus, how it is going to be, that is what we have to take it. So, essentially amplitude of each wavelet we take it, okay, and that depends upon the Coulomb potential. Okay. There are many model potentials which we can use it. One is a screened Coulomb potential which can be used, which depends upon minus Z E squared by R, okay, into e to the power of minus. Then there are Fermi, Thomas Fermi and Rutherford models. There are many types of potentials are there. Okay. There are rigorous calculations which are being done. Okay. As far as the structure factor consideration is concerned, there is a different way in which it has been calculated. That is what I will talk about it. Okay. But if you look at the scattering of an electron by an atom, okay, if the primary electron is entering into the atom which is far away from the atomic core, then what it will happen? It will be a repulsive interaction between an electron. When it is comes close by, it is going to be an attractive interaction. As it is close to the nucleus, if it enters, it will be deviated at large. If it is very close, because it is moving, so what it will happen is that this itself will be, it can come back also as a backscattered electron. All these type of processes which could occur. Okay. So, then essentially what is important is that depending upon that potential which the electron as it enters, whether it enters here or here or here, the potential VR is going to change. Okay. That is what we have to look at it. So, how we can write this? This potential can be written as one, there is an attractive potential which depends upon R, that is what it is, plus there is a repulsive potential away from it. Okay. This way we can write the potential, and if we try to substitute and solve it, the details mathematics one can find, it turns out to be two terms. One is depend upon Z, okay, one term, and another is a factor which depends upon the density of the electrons which are going to the repulsive interaction which is going to be there. Okay. We know that for X-ray the same thing, the atomic scattering factor, if we look at it, only this pre-term C squared by mc squared, otherwise this is the same. So, this term can be substituted, okay, with respect to f delta k divided by the pre-term which is going to be there. That if we substitute, then we will be able to get an expression like this. Okay. And so, both the nuclear as well as the attractive as well as repulsive force, both are going to act. Okay. We can substitute all these values, and this is the sort of an expression which we get it. Now, we know that is Z charge, this has been calculated, and this is for f of theta, how it is going to vary as a function of sin theta by lambda, it is plotted. Here again we can see that as we go away, okay, there is a reduction in the atomic scattering factor. Maximum is in the forward direction. Okay. But now if you should remember that these values no more correspond to the atomic number, but it has a maximum value. For example, if you take copper, and then as the angle of scattering increases, the contribution is going to decrease. So, depending upon the type of reflection which we are using it, we have to use these values in the case of electron, and essentially decrease F decreases with increase of delta K. Okay. We can see it is that if it is for aluminum, okay, the way it is changing. For gold, if you see it, it is not that same, the drop is going to be different. These are all the things which we can qualitatively make out looking at this plot. Okay. Since the same type of behavior we see both in the case of X-ray, for the incident cases where the incident beam is an X-ray as well as an electron, it is better to have look at a comparison between these two. So, in the case of an X-ray, if you look at it, Fx, if you see the way it drops, okay, is rather not that sharp, okay, because this is a normalized plot, okay, whereas in the case of an electron it drops very drastically. Why it happens? Because for X-ray the wavelength is almost the same as that of the interatomic spacing, right, whereas in the case of electron diffraction the energy of the electrons is very high. So, the K is very small, okay, correct, wavelength, and that is why we can make out that these, and what happens in the case of neutrons. Neutron is interacting with the nucleus, okay. The wavelength of the neutron also could be, which we use, is the same as that of the interatomic spacing. But what happens with respect to the size of the nucleus? Each nucleon, it has to interact with it, but the nucleus size is so small compared to the wavelength that from a region like this, okay, if we consider it, if the wavelength is very large, so the phase difference delta K dot R, if we try to find out, okay, this is going to be extremely small. Okay. If that value turns out to be very small irrespective of that angle, then what is essentially is going to happen is that this value of Fn will remain a constant. Okay. So, that is what essentially what is going. This is one of the advantage that in neutron diffraction, okay, the intensity over the angle of scattering which we consider it, it remains almost the same. Okay. Is it clear? So, essentially what we have to look at it is that what we have to consider is that depending upon whether it is electron or X-ray or neutron, okay, how as a function of scattering angle the atomic scattering factor changes is different. The effect is maximum in the case of electron and nil in the case of neutrons. Okay. Suppose now we are coming back to a case of an electron scattering. Okay. In this, if we increase the energy from 100 to 200 keV, okay, then what is essentially is going to happen is that for a particular scattering angle, we can immediately make out that as the energy is increased, okay, the scattering cross section is coming down. Okay. What is going to be the effect of this? This we will look at it. Okay. The scattering cross section is going to come down, means that F is going to decrease, okay, that is one which is going to happen, and if the interaction is going to be less, okay, the probability of elastic scattering taking place is high, inelastic scattering is less. So, even a thicker sample could be used, and that also comes out if you look at the mean free path also. If we try to plot as a function of incident electron energy, we can see that depending upon the atomic number of that element, okay, or even for a specific particular copper, if we see it, that is gradually we see that even for 200 kV, that is here we have to use a sample maybe about 10 nanometer thick. Okay. This is the mean free path, is the means that when the electron enters the sample, between the first collision to the next collision, what is the distance which it will travel. That means that that is where it is going to lose energy inelastically. So, thicker samples could be used. Here again taken from the book. Okay, I am just giving what's the, for 200 kV what is going to be the atomic scattering factor. Here what is essentially important is that if you see here titanium 4 plus, okay, ion or titanium, okay, for small angles if you try to see it, that is a large variation in the atomic scattering factor. Okay. The effect of this is going to be reflected in the intensity of the X-ray, intensity of the diffraction peaks. Okay. This could be used to tell also or to identify that whether which chemical state it is there. If one tries to quantitatively determine the electron intensity, we can do. In fact, the present day microscopes are fitted with detectors, okay, which can almost do every electron could be counted, okay, and the dynamic range is so large that X-ray diffraction pattern. Earlier the problem was getting information from electron diffraction, counting all the electrons, even the central beam is going to be difficult. Now detectors are available with which it could be done, so that we can do one-to-one comparison, okay, and using the diffraction pattern itself we can find out in which sort of a chemical state it is existing. That is also possible in principle. Okay. In the case of neutron scattering, what happens? Okay. Essentially the mass of the neutron is high, so the momentum is going to be, k is going to be high, correct? Momentum is that is what essentially we have to consider it. But the advantage is that since it has got a spin associated with it, okay, we will stop here now.